Hi everyone, welcome on this new video. Today we're going to talk about the black hole thermodynamics and in particular the entropy problem. Before the video starts, I advise that you adjust the playback speed to probably 1.25 if you want a bit more fluidity. All right, let's start then. So we know that black holes are very strange objects, and in a thermodynamical point of view, there is a problem called the entropy problem. So in thermodynamics, we know that the universe has a total entropy, which we called S total. And we know that this entropy can never decrease, which means that a differential of that total entropy must be either null or positive. So if the universe has a total entropy, it means that a black hole, pH for black hole, must be associated with some entropy too. Yeah, which I will call S for entropy and BH for black hole. All right. From thermodynamics, you might recall that ds over dE, a differential of energy, is equal 1 over temperature. So that's a thermodynamic law for any object in the universe, meaning that if black hole has entropy, which it must have, so it also must have a temperature. So black hole must be associated with a temperature T black hole. Now we know that any object in the universe with some temperature must radiate. It's the black body radiation. So this leads also to black body radiation. But by definition, a black hole does not radiate because it's a region in the universe where nothing can escape, not even relativistic particles and light. So you might argue that maybe the temperature of the black hole is 0, but we see from there that if T equals 0, then if T equals 0 for a black hole, this implies that the entropy of a black hole must be infinite. And this is not acceptable, or at least it's unphysical for many reasons. So we're not really satisfied with that idea that black hole has no temperature. Therefore, we have a problem, just the entropy problem, because we're trying to associate the black hole with an entropy, but this leads to a temperature, and temperature telling us that black hole must radiate, but we know that black hole does not radiate, so we have a problem here. Okay. There is a conjecture. It has been proven in few cases, but not. It's hard to prove for a general case. But it's believed by a lot of physicists that any equilibrium black hole is fully characterized by the mass, the angular momentum, and the charge. So this is a conjecture, or it's called the no-hair theorem. And equilibrium black hole. So after their formation, when they stabilize and they get to equilibrium state, they're fully described or fully characterized by the mass, the angular momentum, and the charge. So we can rely on this first theorem, or rather conjecture. And another one is Hawking's area theorem, which says that the total black hole area can never decrease. So Hawking classical area theorem, which say that if you take the area of every black hole in the universe, this total area A will never decrease. So a differential of area must be positive or null always. And this theorem depends on unproven but rather reasonable assumptions, such as that there exists no naked singularity. If there is a singularity, there must be some event horizon, and we can never access the singularity, or we can never observe it directly. Okay. The area, of course, is a function described. It's a function that depends on mass, angular momentum, and charge, because those are the only freedom we have. And this leads to the first law of black hole thermodynamics, which shows that a differential of mass must be equal to a differential in area plus a differential in angular momentum plus a differential in charge. This is the first law of black hole thermodynamic. This is the surface gravity. It's a scalar that you obtain by considering that at the event horizon of a black hole, so at the surface of a black hole, the gravity is infinite, but infinitely far away from this black hole. So if we observe a black hole from Earth, for example, this gravity is also infinitely redshifted. And so if you multiply this infinite gravity by the redshift factor, you obtain a finite scalar that is called surface gravity, kappa, and is a function, again, on the mass, angular momentum, and the charge. This is the angular velocity. and this is the electric potential. And we could see Zero's law of black hole thermodynamic that says that surface gravity of stationary black hole is constant. So kappa of stationary black hole must be constant. This is the Zero's law of black hole thermodynamic. And then we can write the first law of black hole thermodynamic. All right. So these are some tools that we can use to understand better the entropy problem. So now if we go back to the entropy problem, what could be the entropy of a black hole? Well, we're tempted to say that, sorry, the entropy of a black hole must be proportional to the area, because the area is a function of mass, angular momentum, and charge. And we see that from Hawking's area theorem, it cannot decrease, just as the entropy of a black hole should also not decrease. So we're tempted to say that its entropy must be proportional to its area, and therefore kappa, as we see here in this relation, must be proportional to temperature. This is because this first law of black hole thermodynamics can be compared with the first law of just thermodynamics. So we know that M, the mass, we know that it's equivalent to energy, and the black hole and the thermodynamic first law is dE equal TdS. So we see that, sorry, we see that we can relate S to A, entropy to area, and we can relate kappa to the temperature. And of course, the first law of thermodynamics. Then there is also the work term, which is PDV, and this we never consider it in thermodynamics. But if you have a rotating object, then you must consider the angular velocity d and the differential of angular moment. This is the first law of thermodynamics. All right, so if we go back to the entropy problem, then we can say the entropy of a black hole must be proportional to its area, and its surface gravity must be proportional to its temperature. And actually, this is what Hawking's shown later using quantum field theory, QFT. So implementing QFT in the equations of general relativity, Hawking showed that indeed the entropy of a black hole is equal to its area divided by the Planck area. In geometry's unit, it's this. And its temperature, so Boltzmann constant times the temperature of the black hole, it's equal to its surface gravity divided by 2 pi. So implementing QFT in general relativity is implied that if that black hole has entropy and thus black hole radiates. So black holes are radiating, are at a very slow rate. But the classical Hawking's area theorem was saying that the area could not decrease. And now we say that black holes are radiating, so actually area is decreasing at a slow rate if the black hole is radiating. So we have to come up with a law that will replace this classical area theorem, and that's the second law of thermodynamics. I wrote in like, yeah. So the second law of thermodynamics is that if we consider a differential of the total entropy of the universe, then it's equal to the entropy of the universe plus the entropy of black hole. Sorry, differential. And it's this total entropy that, according to thermodynamics, cannot decrease. This is the second law of black hole thermodynamics. All right. So I think that's all. The conclusion is that Hawking's radiation is solving the entropy problem. A black hole radiates and is associated with an entropy proportional to its area. The temperature of a black hole is associated with the surface gravity. But this leads to a more important problem than the entropy problem. Now that the entropy problem is solved, the fact that black hole radiates leads to the information paradox, which I will not talk about it now. So maybe I just want to make one last point about Hawking's area theorem. Yes. So here we use the conjecture that black hole must be described by the mass, angular momentum, and their charge when they're at equilibrium. And we use the Hawking's area theorem, and the Hawking's area theorem that a black hole cannot decrease, the area of a black hole cannot decrease, comes from the fact that the only way a black hole could decrease is either by more non-escaping light rays entering the black hole. I mean, the only way that a black hole could increase. Yeah, I should stop the video actually. Thank you for watching.